All right, guys, so this is our last graphing of transformations video. In this video, we're going to talk about non-rigid transformations. So these are transformations of the graphs of functions that are going to change the size and shape. And we're going to see these transformations as stretches and shrinks, and we are going to see them happen vertically and horizontally on the xy axis. So first, what we're going to look at is horizontal stretches or shrinks. So right here, for a horizontal stretch, we see a multiplication by a number less than 1 inside the function. When we talk about a number less than 1 inside the function, some number a, we're actually talking about a number really in between 0 and 1. And when we talk about multiplication inside the function, we're talking about multiplying that a directly to the x value, right? So right here, let's take a look at an example. We've got f of x, and then we're seeing the x inside f being multiplied by 1/2 in the equation over here. So basically everywhere where we would have an x in our f of x as x cubed minus 3x, we're seeing that x being multiplied by 1/2 inside the function. So let's take a look at this. Let's compare some ordered pairs here for our two equations. So right here, let's say we've got x equals -1. If we plug that into our function f, you guys can do the math out, but f of -1 is going to turn out to be 2, right? So we're basically seeing the x value of -1 give us the function value of 2, and we get that local max right there. So what we could ask ourselves over here is, what x value am I going to have to plug into f of 1/2 x in order for that f to evaluate -1 and give me the max of 2? Well, right here what we can see is we're actually going to have to plug in a -2 into our f of 1/2 x. We get f of 1/2 times -2, giving us f of -1, which gives us the max of 2. So right here, we're seeing actually the ordered pair that gives us that max value of 2 happen at the x value of -2. So right here we've got the max happening over at -2 on the x-axis instead of that -1. And in general, what we can think here is when we're multiplying by a number in between 1 and 0 with our x inside the function, we're seeing a slowing down of those x values, right? And the entire function is happening over a longer period on the x-axis, right? And we can see the same thing happen on the positive x-axis over here. We're seeing that min happen much later on the positive x-axis. In general, what we can see here is that the function is taking twice as long to happen on the x-axis because every x value is being multiplied by 1/2, right? And so we can say that the transformation we're seeing here is a horizontal stretch by a factor of 2, not 1/2, but 2. This function is now twice as wide as it was before. It's taking twice as long to happen on the x-axis. And right here, what we want to notice is that that 2 is actually a reciprocal of the number we're multiplying inside the function by. So right here, we can say that in general, this is always going to be a reciprocal of that a value. Okay, so looking at horizontal shrinks, we can say that horizontal shrinks happen when we multiply by a number greater than 1 inside the function. So right here we can again call that number a, and we're talking about a being greater than 1 in this case. And when we multiply inside the function, we're talking about multiplying a and times x directly to x inside the equation, right? So right here we've got our same function, f of x equals x cubed minus 3x, and now we're multiplying by 2. We're multiplying that x by 2 inside of f. And right here we can do the same thing we did before. We can sort of spot that local max that we get when we plug in the x value of -1. F of -1 is, of course, 2, right? We get that local max of -1, 2. And again, we can ask ourselves, right here, what x value am I going to have to plug in to f of 2x in order for f to evaluate -1 and give me that max of 2 again? So right here, what we can see is that that x value is going to have to be -1/2. And f of 2 times -1/2 is going to give me f of -1, which gives me the output of 2. And now we're seeing that max happen much faster on the x-axis, right? And in general, again, what we can say is this multiplication directly to x is happening, is affecting the rate at which f is able to process the x values. With this multiplication of 2, we're actually seeing the function process the x values much faster. And the function is happening on a shorter interval on the x-axis, right? Now, we would say that we have reduced the width of the function by 1/2, again, reciprocal of 2. So right here we can say that this is a horizontal shrink by a factor of 1/2. And of course, right here, we can see that that 1/2 is a reciprocal of the a value. So when we're talking about these horizontal stretches and shrinks, we want to think that they're happening by a reciprocal of the number we're multiplying inside the function, right? We multiply by a number greater than 1, right? You might think that that would be twice as wide. Actually, that's happening twice as fast, so it's a horizontal shrink. We're multiplying by 1/2, a number less than 1. You might think that that would maybe be a shrink, but actually that's slowing down the x values so that they're happening over a longer period on the x-axis, and it's a horizontal stretch. All right, so counterintuitive with the horizontal stretches and shrinks, the vertical stretches and shrinks are much easier to see. Right here we can say that we have a vertical stretch when we multiply the entire function, right? And here we're talking about the equation, by a number greater than 1. So right here, a is greater than 1 in this case. Now right here, we've got our same function, f of x equals x cubed minus 3x. And over here, we're multiplying that function by 3. Now, remember that that equation is really defining the y values, right? So we've got ordered pairs x, y here, right? And over here, we've got that same equation defining the y values, and then we're multiplying all of the y values this equation gives us by 3. So now our ordered pairs look like x, 3y. And what we're seeing here is a vertical stretch. Right here we've got the ordered pair -1, 2, right? That ordered pair is happening at the same point on the x-axis, -1. But now that y value has been multiplied by 3, so we get -1, 6 as that local max. And similarly, right here we would see this function value be 3 times its previous value, and we get the graph looking something like this. Where the entire graph is vertically stretched by that factor of 3. And right here we would write this as a vertical stretch by a factor of 3. Notice, not the reciprocal, the actual number for vertical stretches and shrinks. So right here, looking at a vertical shrink, right here we've got shrink is going to happen when we multiply the entire function, and again that's the equation, by a number less than 1. And again, when we talk about a number less than 1, really we're saying a number in between 0 and 1. So right here, same example, we've got f of x equals x cubed minus 3x. When we multiply this function by 1/2 now, we're seeing the y values defined by this equation, giving us the y values, the ordered pairs. We're seeing those y values same y values, now multiplied by 1/2. So now the ordered pairs look like x and then 1/2 of the previous y value. So basically, we're taking all of those y values and cutting them in half, and we get a graph that looks like this now. Now, one thing we can notice here is that the function values at the origin are staying the same, right? When I multiply 0, the function value of 0, which is a y value, right, by 1/2, it stays 0. When I multiply the function value of 0 here by 3 times 0 is still 0, right? And right here we can say down here that this, of course, is a vertical shrink by a factor of 1/2. Right? So pretty intuitive. When we multiply outside the function by a constant, we see those vertical stretches and shrinks by a factor of the number we're multiplying by. Okay, so let's talk about some compositions of transformations. When we start composing transformations inside the function, things get a little complicated, and we want to address that complication. So right here we've got a function f of x as the square function, right? And we're seeing a collection of transformations happen inside that square. So what we want to do is talk about what's going to happen to that graph of x squared, which we're seeing over here, right, with these transformations. Now, immediately, we see the addition of 12, right? And you might think that that addition of 12 is going to take us 12 in the negative direction, which we can think about it as doing, right? And we get that same graph, right? Now moved 12 in the negative direction. So it's the exact same shape. Now we're looking at the multiplication of 3 inside the function, and that's going to be a horizontal shrink, right? Now that's going to be a horizontal shrink for every value around the y-axis. So basically what we're seeing is this function pulled towards the origin, right? And now that that x value of negative 12, where we're seeing the vertex, is now happening at 1/3 the width. So it's actually happening now at negative 4. So as this graph is horizontally shrunken, the vertex moves in to 1/3 the x value, which is that negative 4. Now, to my mind, this is a more complicated way to see this. One thing we can sort of see to sort of spot this is, remember that the x squared, right, is going to give its vertex when it evaluates 0, right? So right here we can say that where 3x plus 12 equals 0, right, that's going to be the x value where we see our vertex. And if we solve for x in this case, we get negative 4. So we can sort of spot this happening already. But in general, what I want to do is show you the way that I evaluate transformations when I see a collection of transformations happening inside the function. And what I do here is I redefine g of x, right? What I'm going to do is I am going to factor everything off of x inside the function, right? So I'm basically going to factor away anything that's happening to x to everything that's happening inside the function. So right here I would have g of x equals, and then 3 times x plus 4 squared. Now, what we can see is that horizontal shift, 4 in the negative direction, right, as it's happening directly to x. And actually what we're able to do is evaluate these transformations from x out. So right here, the first transformation I'm seeing is that horizontal shift that takes me out to negative 4. But what I want to think now is negative 4 is where the function thinks the origin is. So when I evaluate this horizontal shrink of 3, it's going to happen at x equals negative 4. It's not going to happen around the origin. So right here, basically, I can see this as the function getting skinnier at x equals -4. Now, evaluating these transformations, what we can say is that shift is basically left 4, right, or 4 in the negative direction, and then that horizontal shrink that we're seeing would be a horizontal shrink, and then I would say around x equals -4. Now, I might not always say around x equals -4, but for some other transformations that we're going to look at pretty immediately, that we are going to have to specify where they happen on the x-axis, and that's where the function thinks the origin is, right? The square is evaluating 0 at x equals -4. I have to plug in a -4 in order for the square to evaluate 0. So let's take a look at this next one. Right here we've got the function as the square root function, right? And g of x we're going to get basically by evaluating the transformations from inside the function and talking about the transformations that they give our graph f here. So why don't you guys go ahead and give this one a shot, and we'll come back in a minute and look at it together. So why don't you pause the video. Okay, so right here, the first thing I'm going to do to see all my transformations is I'm going to factor everything that's happening to x off of the inside of the function. Basically what I'm saying is I'm going to factor everything away from x from that inside expression, right? So now I've got the square root, and when I factor off not just the 2, but the negative as well, I get -2, and then right here I'm going to get, we'll say it's x, and then minus 3. So immediately I can see that the function is going to evaluate the origin at x equals +3. That subtraction of 3 is a shift of 3 in the positive direction horizontally. Well, that didn't quite work out. And now I can step outside of that, right, evaluating from x out, and evaluate the transformation of the multiplication of 2 and the negative inside that root. Now, the first thing I'm going to do is I'm going to evaluate the negative. Really, we could sort of think of this as almost a multiplication of -1 and a multiplication of 2. The evaluation of the negative I'm going to evaluate first because it's a rigid transformation, and I can sort of move my graph without actually changing its shape at all. So right here, that negative inside the function means I'm going to see a horizontal reflection, but that horizontal reflection is going to happen where the function thinks 0 is, which is +3. So right here, we flip this guy, and we're going to flip him left to right, and that's going to make him look like this, right? And then that last transformation I'm going to evaluate is the multiplication of 2, which is a horizontal shrink, and that's going to make it look something like this. You can graph this to take a look. I might have been a little bit generous with that horizontal shrink. I'm going to take this guy away. But that green graph should be approximately what we're seeing right here for the graph of our function. If we're evaluating these transformations, first we would say right 3, and that's sort of an abbreviation. I'm fine with you guys giving me those abbreviations. I want to, and then right here, if we evaluate that negative, we're going to say that's a horizontal reflection. And again, here we want to be specific at x equals 3, right? Because it's not a horizontal reflection over the y-axis. It's a horizontal reflection where the function thinks the y-axis or the origin is. And then finally, right here, I'm going to evaluate that that multiplication of 2, and that's going to be a horizontal shrink of right here 2. Now, when we're talking about vertical transformations, they're all very straightforward. You can evaluate with basically order of operations from the outside of the function out. But these horizontal transformations, we have to watch out for the horizontal shift that we're seeing first and evaluate that. One thing we can also sort of take a look at here is this graph is a horizontal shrink by a factor of 2. Whoops. If it's a horizontal shrink, it's going to be a horizontal shrink by the reciprocal 1/2. It's a horizontal shrink by a factor of 1/2, but it also looks like it could be a vertical stretch. And what I want to do right now is talk a little bit about the relationship between those two things. So right here we've got, let's say, y equals x squared, right? Now let's say I want to take a look at the horizontal shrink of 1/2. So right here that would mean y equals, and then I multiply inside my square by 2, right? That's horizontal shrink by 1/2. We're multiplying by a number greater than 1, and it's going to be a shrink by the reciprocal. Now, what if I simplify this? So right here, I can distribute the square to both the x and the 2, and that's going to turn into 4x squared. Now this is a vertical stretch by 4. So here what we're seeing is that horizontal shrink by 1/2 is actually equivalent to that vertical stretch by a factor of 4 for the square. Now it's not always true that we see that relationship between a horizontal shrink of 1/2 and a vertical stretch by 4, but generally there can be a relation between a horizontal shrink and a vertical stretch, or a vertical shrink and a horizontal stretch. Okay, so we've got 3 problems that I want you guys to take a quick look at. Right here, I want you guys to list the transformations that we're seeing from our first function to our second function for all 3 of these guys. We'll come back in a second and evaluate. Okay, so right here, looking at this first guy, I've got a multiplication of 0.5 inside the function, which is the square root. Now, there's no horizontal shift, so I don't have to worry about factoring anything off of the inside of the function. I can just go straight to evaluating the transformations. Right here, I can say this is a horizontal stretch by 2, right? And that's, of course, happening around the origin, right? And then right here, we've got the addition of 2 on the outside, and I would just say, hey, that's up to, right? Up to pretty much implies a vertical shift, and we can say up to is good enough for us. All right, so looking at this next guy, we're seeing a negative on the x inside the function. So to evaluate the transformations, what I'm going to do is I'm going to call this guy y equals 4, and then I'm going to factor the negative off of the inside and say that is x. And then right here, that would be minus 6. Since I'm factoring the negative off of the 6 as well, it becomes negative, right? So at this point, right here, we can evaluate the transformations from x out. So right here, from x out, we see our function first go right 6. Then the next transformation is that flip that we're seeing from the negative, and it's going to be a horizontal flip at x equals 6. So right here, we can say horizontal, oops, flip or reflection. Flip and reflection, we'll say, are basically the same thing. They're the same motion. At x equals 6. Now finally, we've got that multiplication of 4, and that's a vertical stretch by 4. And that's all the transformations we're seeing, right? Subtraction of 6, horizontal flip, and then the multiplication of 4 is a vertical stretch by 4. Okay, so for this last guy is a little bit tricky. We're talking about the transformations that we would need to do to go from this graph to this graph. And what we're going to do here is we're going to talk about the transformations that we see from the start, and then compare them to the transformations we're seeing here at the end. And those are transformations from x squared. So right here, first what we can say is we start by moving it right 2 and having a vertical stretch of 2, right? From there, we're seeing a shift that is going to be left 3, and basically a normal graph. So basically the same shape as basically just the x squared. So right here, from the start to the end, we've gone from right 2 to left 3, so that means we've gone left 5. And right here we've gone from a vertical stretch of 2 back to normal, so that means we are vertically shrinking by 1/2, right, in order to get that graph back to normal from a vertical stretch of 2. All right, guys, so that's the video. We will work on a worksheet tomorrow in class, and we will see you then.